In this video, I'm going to talk about the SOLID principles. This is an acronym for the 5 principles that I'm going to talk about here. They are the single responsibility principle, the open-closed principle, the Liskov substitution principle, the interface segregation principle, and the dependency inversion principle. There's a lot of highfalutin talk here. We're not going to show any code samples in this video. I'm just going to talk to slides. Before I get going, a quick fun fact. A lot of these principles were espoused by a famous programmer named Uncle Bob Martin, who was one of the authors of the famous Agile Manifesto. He's written many, many books and articles on these subjects, so consult those if you want more details. I am just going to go over these in a very sort of simplified way. Each of these principles that I'm going to talk about could be the topic of an entire course themselves, right? There's a lot of depth here. And also, they can all be taken to ridiculous extremes. I have many times had people tell me that, oh, well, we're designing this particular set of classes here in order to be solid and not in order to actually provide value to customers, which seems to, or to save shareholder money or something like that, right? The solid principles are all good, but you want to be sure that you're keeping your eye on the end and not the means. These principles, they're all designed to lower the cost of changes. Remember, we talked before about how software is complex, and one of the reasons why software is complex is because so many people want it to change so quickly, so much of the time. Applying these principles also comes with costs, right? So also always make good cost-benefit decisions when you're trying to figure out how to apply these solid principles. And also, it really helps to, when you are designing a software package originally, to try to figure out how is this thing going to change in the future? If you're designing a game, then you might want to think about, well, are we going to want to add downloadable content to this game? If you were designing a system that does tax reporting, you might say, well, how are we going to modify this system in the future when the tax law changes? You want to be thinking about what kinds of things can change, what kind of things can stay the same, and apply these principles accordingly. So let's just go through the 5 principles. And again, I'm just going to give a very brief overview of each. So the single responsibility principle comes down to a class should really do one thing. It should be the expert at one thing. Every class has one responsibility, and no other class shares that specific responsibility. So a good way to think about have I violated the single responsibility principle is to say, if I want to make a bunch of changes to my program, how many classes do I need to change in order to do that? So if you're writing a game where a wizard can attack a werewolf, and you want to change the sound that happens when that attack happens, and you want to change the bonus that happens when the wizard is using a particular special sword, right? Do you have to make, in order to make those 2 changes, do you have to change 2 classes, a dozen classes, 100 classes? Do you have to say, oh, well, we're changing the code so that a wizard can attack a werewolf, and therefore we have to also change the code that where a warrior is attacking a dragon, and also we have to change the code that bills the customer, right? That would be an egregious violation of the single responsibility principle. There should be one place in the code that you have to change in order to effect a change. All right, so what about the open-closed principle? The basic idea of the open-closed principle is you want to think hard about how you're designing when inheritance is involved. You want to design your classes to be open to extension, but closed to modification. And what do we mean by open to extension, but closed to modification? The idea is if you need to make a change to your class, you need to make some customization to it. Can you do that by, let's create a derived class? In our previous example, we said, oh, we wanted to add the word president before the string representation of a name, right? Well, can we make a derived type that then changes the behavior of toString in some specific way, right? Or do we have to go back in and make modification to the base type, to the person type, in order to affect that change, right? So the idea of the open-closed principle is be open to extension, allow inheritance, allow methods to be overridden virtually, but closed to modification. Don't require that people who want to change your type have your source code and actually change the source code of the base type. Now, I actually slightly disagree with the open-closed principle. I think it's going in the right direction, but this is one of those principles that I think can be overused, because I think inheritance is often overused. And the argument that I give is, well, why do we stop at inheritance? Right? We've already seen that you can have features of base types that we mark as private. Right? We can say, well, this property can be read, but it cannot be written. Well, doesn't the open-close principle say that, well, what if somebody wants to write that property? Right? Do they have to create a derived type that has a writable property? Shouldn't they be able to just write it into the base class if they want? But now that's something that you have to test. Right? So I prefer thinking that code reusability is a feature, and that has to be budgeted and prioritized and designed and implemented and tested just like any other feature. And so think very carefully before you say, you know what, I'm going to make my class wide open to extension by anybody who wants to extend it, because you might be providing something that's actually not giving them the features that they need in order to effectively extend your class. Those things have to be designed in. We're going to talk about this more in the next video. The Liskov substitution principle. This is one of the more sort of highfalutin computer science principles. But basically, it comes down to a giraffe is a kind of mammal, a mammal is a kind of animal, an animal is a kind of thing. If you write some code that takes a mammal, then it must function correctly when you give it a giraffe, and it must function correctly when you give it a tiger. Basically, the Liskov substitution principle is that polymorphism has to work. You have to design your programs so that they are not saying, well, I said this method takes any mammal, but in fact, I only accept tigers, ocelots, and platypuses. I don't accept giraffes. Right? So if you are writing a base class, then you must clearly communicate what conditions must be met by any instance of that class to the author of a derived class. Right? So that if you create a base class, animal or mammal or whatever, and somebody writes a method that uses that mammal, right, then if you are the author of the mammal class and you know that somebody else is going to be the author of the giraffe class, you have to tell that guy, you know what? Code that uses this thing as a mammal is going to expect that this thing can have hair and give birth to live young. Right? So don't be writing some kind of class over here where those conditions are not met, because otherwise this bit of code here is going to fail. The interface segregation principle is basically avoid really obese classes. The classes that we've been looking at so far have been pretty small, but you remember from a few episodes back we started writing a class that implemented the Hangman game. That class might be doing too much. It might be violating both the interface segregation principle and the single responsibility principle. And we'll look at that in more detail later. But basically, the idea here is if you have a base class, again, let's use animal as our example, then that base class should not have methods like produce milk and lay eggs. Right? The produce milk method should go on the derived type mammal. The lay eggs method should go on the derived type bird. And you could see how, if we did have a base type that had both produce milk and lay eggs, that it becomes bug prone. Right? The giraffe type inherits from animal, and then it overrides the virtual lay eggs method, and now you have a giraffe that can lay eggs, and it just all becomes bad. Right? What you need to do is you need to segregate the surface area of your classes into smaller ones. And there's a bunch of different ways to do that. You can do it through the kind of subtyping that I just described, right, where you have an animal base class, and then you say, well, we're going to put produce milk on a mammal subtype, and we're going to put lay eggs on a bird subtype, and so on. But that can be a bit tricky. I showed an example a few videos back where you end up in a bad situation where you're trying to say, well, military vehicles can do this, and air vehicles can do this, and bicycles can do that, and it gets very, very messy when you have vehicles that are not easy to classify as military or civilian or land or water or whatever. Right? And particularly in this little example here, you think, well, wait, shouldn't reptile have a lay eggs method as well? And now we have both bird and reptile having a lay eggs method, and right. The way to solve this problem in C# is to use a feature called interfaces, which is why this is called the interface segregation principle in part. And we're going to discuss them in a later video. And the dependency inversion principle is essentially a program against abstractions. And it's kind of a highfalutin term for what's really a pretty simple concept. And that is if a class uses the services of another class. In other words, if it calls the methods of another class in order to have some side effect performed or some calculation performed, then it should take in an instance of that class in its constructor rather than creating one. So the example is in our Hangman class, you recall that we created a word list, and then eventually we're going to write code that chooses a word from that word list. Well, that's a service. Right? The word list is providing a service to the Hangman class. It's providing a list of words to choose from. Maybe the code that is using that class, is creating the instance of the Hangman class, should be passing the word list in, rather than relying upon the Hangman class to do that thing. And maybe we should use the most abstract possible way of talking about a word list. Right? Does it have to be an array of strings? Does it have to be a list of strings? Can it just be a sequence of strings? How is that going to work? And again, this is usually done with interfaces, and we'll talk about those in a later video. Now, there's a lot of pros and cons to the dependency inversion principle. On the pro side, it makes your classes super customizable, because anything that you need to do, any service that it needs to consume, you just pass that thing in. It can make some of the individual methods in your classes much simpler. And it can make some testing scenarios simpler, because one of the things you can do with the dependency inversion principle is to say, you know what, this class needs to talk to a database. For our test purposes, I'm going to pass in a service that's a fake database. That's a test version of our database. And now we'll see if this class can handle the test version. Or you say, I'm going to see what happens if I can inject failure. Right? I'm going to say, well, I'm going to give you a version of the database that's not a real version, and that is going to produce predictably a failure at a certain point, and I'm going to make sure that your exception handling works in the case of that failure mode. Those kinds of things can be very difficult to test if you don't have dependency inversion. On the other hand, constructing objects becomes super verbose. And sometimes you end up with objects that are taking in so many other objects as services, and those objects are in turn taking in other objects as services, and so on. The number of combinations that you have to test for your failure injection cases, for your real world cases, can become quite high. And sometimes the code just gets so abstract that it gets really hard to understand. So I find that the dependency injection principle is sometimes misused, and that really it works best in very large-scale components, where you're working at industry scale, where you're working with large databases and things like that. So don't go overboard with this one. All right, so summing up, we have seen the 5 solid principles of object-oriented design. There are, of course, many other principles of object-oriented design, but these ones are often called out as some of the principal ones. So just to reiterate, classes should do one thing and do it well. Code reusability is a feature of that code, and it has to be designed in carefully. A derived class instance can always be used anywhere that a base class instance is required. You should keep methods that are meaningful only in derived classes out of your base classes. You don't want your giraffes laying eggs. And you should consider, when you're designing a class, if that class depends on another class for a particular service, maybe it should be providing some way for that service to be passed in, rather than creating one out of whole cloth.